Okay, so welcome to the, I think this is the third lecture of structure analysis. Okay, before we proceed any further in structure analysis, we need to understand are we going to draw shear force diagram and bending moment diagram. Okay, actually it is a topic of strength of material, but in structure analysis, the final outcome that you have to draw is your shear force diagram and bending moment diagram. So you need to understand what is the meaning of shear force and what is the meaning of bending moment and how are we going to draw these diagrams. Okay, so our objective of this lecture is to understand how to draw shear force diagram, that is SFD, and bending moment diagram. Okay, this is our objective. So before we proceed, let's see a couple of cases. What is shear force and what is bending moment? Okay, shear force as it is defined, it is nothing, it is the resultant of forces, or rather I am saying it is the resultant of lateral forces. Okay, lateral forces on the left or right of any section. The meaning of this definition is, suppose I am having a simply supported beam here. Okay, simply supported beam I am having, this is your pin joint and this is your roller, and suppose I am having some loading here, say P. Okay, now you know the reactions that you will get here is P by 2 and the reaction that you will get here is P by 2. Suppose somewhere around this section AA, okay, I want to cut this beam. Okay, if I cut this beam, what will I get? I am cutting the beam like this. I want to see what is happening at this section A. Okay, so here you will have P by 2, somewhere here is P, and somewhere here you are having P by 2. Just drawing the free body diagram. Okay, now some forces will come at this section and some forces will come at this section. Okay, so if you see at this section, okay, to have equilibrium of this part, okay, equilibrium of this part suggests that your vertical forces net should be 0 and your net moment, okay, about z axis should be 0. X forces are already 0, so you don't need to use your sigma fx equal to 0. It is already satisfied, okay, because there is no force in x direction. Okay, you have P by 2 in the upward direction, so it is obvious that you will get one force P by 2 in the downward direction to balance this force. Okay, to balance this force, you will also get a moment. Okay, you will also get a moment because you know moment about this joint here is 0 because it is a pin joint, isn't it? Because it is a pin joint. Now suppose I am having a moment M like this. Okay, can you find out the moment M? Of course you can find out. You have this point A. Okay, A is your pin joint. Okay, at pin joint your moment is 0, so your net moment at A is 0. Is it okay? So what are the moment producing things on A? You have P by 2. Okay, suppose this distance is, suppose x. Okay, so you will get at A clockwise moment of P by 2 into x, and your anti-clockwise moment of M plus M is equal to 0. So your M will come out to be how much? P by 2 into x. Is it okay? P by 2 into x. Now to have this internal equilibrium here, okay, since you applied P by 2 downwards here, you have to apply P by 2 in the upward direction here. Okay, and opposite moment also you have to apply equal to M. Is this okay? So shear force is equal to this P by 2. Is it okay? This type of forces, lateral forces that exist, are called as your shear force. Okay, suppose I am drawing this section here. This force that exists here, V, is your shear force, and this force that exists is your bending moment. Okay, this is your shear force and this is your bending moment. Okay, so I think you are able to understand. You already know what is shear force and bending moment. I am just brushing up. Okay, before we go any further, let's assign, or let's just have a sign convention that we are going to use for our bending moment and shear force. Okay, suppose you have a beam like this, okay, and the rest of the part is here. Okay, your entire beam is something like this. You have pin joint here, roller here, okay, and some loading is there. Okay, some loading is there. I want to find out what is the forces existing at this section AA. Okay, so I cut this beam like this. Okay, I cut this beam like this. Obviously you will have some reaction here, some reaction here, okay, and you will have some shear force here, V, and some bending moment at this section. Is it okay? Opposite direction to this, you will have on this section shear force and bending moment. Okay, so I am clearing your doubt once and for all. Those who are having doubt in sign convention, okay, this is the right sign convention. Okay, now this, okay, on left section, okay, this is your left section and this is your right section. Okay, on left section, shear force is positive in downward direction. Downward direction. Throughout shear force, bending moment and structure analysis, we will follow the same sign convention. So listen very carefully. Okay, on left section, your moment, okay, is positive as shown here. Okay, or rather I am saying moment is positive in anti-clockwise direction. Anti-clockwise direction. Okay, on right section, if you talk about your right section, sometimes you have to go back from the right section. Okay, so from right section, V is positive in up direction. Okay, up direction, and on your right section, your moment is positive in clockwise direction. Okay, no need to remember the statements, just remember this. Okay, remember this. On left section, your downward shear is positive and anti-clockwise moment is positive. Opposite to that, this scenario is also positive for the right section. Is it okay? So I think you are able to understand the sign convention that we are having. Okay, now before we proceed any further, okay, we have to establish a relation between, okay, shear force, bending moment and loading. Okay, V is your shear force, okay, M is your bending moment and W is your loading. Okay, what is the convention for W? Okay, that also you can note. For loading W, okay, downward is negative. Is it okay? And vice versa, upward is positive. Okay, now let's establish a relation between shear force, bending moment and W. Sometimes in interview this type of things are asked. Okay, derivations are asked. So suppose you are having a very big beam like this. Okay, it is simply supported here. Okay, and then you are having some loading like this. Okay, suppose I am talking about a small section, this much section I want to talk about. Let this length be delta x. Is it okay? Let this length be delta x. Now I want to talk about this small part only. I want to talk about this small part only. See carefully, you are having your loading here. Okay, loading is suppose W. Okay, you will have some shear force and bending moment. I have already told you, take positive convention. Okay, you will have shear force here and bending moment here. This is your right section here, so you will have shear force here and some bending moment here. Okay, since you have moved delta x distance, this moment will be increased m plus dm. Is it okay? M plus dm. Now consider the equilibrium of this small element. Consider the equilibrium of the element. Okay, equilibrium, we can say three equations. We can say, you can say sigma net forces in x direction is 0, next forces in y direction is 0, and net moment about O, any surface you can take, is equal to 0. Is it okay? Now sigma fx equal to 0, this is of no use to us because there is no horizontal force. Okay, we have no horizontal force, so this equation is useless. We want to use this equation, sigma fy equal to 0. Okay, sigma fy is equal to 0. Okay, what are the forces that you are having? You are having a vertical force W, okay, and you are having shear forces, isn't it? You are having shear forces. Okay, this is also V plus dV, isn't it? This force will be V plus dV because you have moved some distance dx, so your shear force has changed. Okay, it is slightly increased. So if you use the equilibrium, you have minus W into delta x. Okay, delta x or dx you can say, minus W delta x because it is in the downward direction. Okay, minus W delta x plus V, okay, minus V plus dV or delta V, whatever you want to say, is equal to 0. Is it okay? If you solve this, okay, if you solve this, what you will get? V is equal to, okay, or rather you will get dV is equal to minus W dx. Okay, delta x I am writing dx. Okay, that is the same thing. So you can write your W is equal to, or how should I put this? W is equal to minus dV by dx. Is this okay? So this is the first relation between your loading and your shear force. Second thing that we want to do is we want to equate moment equal to 0. So what you can do, at the center point O, okay, at the center point O, you can equate your net moment to 0. Is this okay? Okay. So you can say this shear is producing a couple equal to V dx, okay, and the net moment that you are having m plus dm minus m, so you are having dm amount of moment, so you can say your shear is equal to how much? Dm by dx. Is it okay? Dm by dx. So you have your relationships here. Okay, I am finally summing up the relationships. You have two relationships. Your W, sine you don't take, okay, sine will be taken later. Your W is equal to dV by dx, okay, and your shear is equal to dm by dx. Okay, these are very important relationships and we will use them while drawing shear force and bending moment diagrams. Okay, now let's start drawing a couple of shear force and bending moment diagram. First, what I want to tell you is the classical approach. Classical approach to draw SFD, okay, and BMD. Is it okay? What is the classical approach that we use to draw shear force diagram and bending moment diagram? For that, I am taking, suppose, a simply supported question. Okay, this approach we will not follow. We will use a shortcut approach, okay, which is a quicker one. Okay, that we will use. This approach is just for just in case you get stuck, okay, somewhere, so you can always go back to your classical approach. Okay, I want you to draw shear force diagram and bending moment diagram of this beam. Okay, so from now on, the approach that you should follow is, okay, you should always draw your shear force diagram just below this beam, exactly below this beam. Okay, and below your shear force diagram you can draw your bending moment diagram, okay, like this. Okay, you always keep in mind, you draw it like this. Here always you draw your shear force diagram, and here you draw your bending moment diagram, and here you can keep your original beam. This is how you draw your bending moment diagram. Is it okay? And whatever rough work is required, you do it in the side. Okay, now this is your beam P. Okay, you will have reaction here P by 2 and P by 2. Okay, what is the shear force at the starting point? Suppose I am starting from the left point. Okay, what is the shear force here? Is it equal to P by 2? Okay, is it equal to P by 2? Obviously it is equal to P by 2. you take just the left section. Okay, here you are having P by 2, so here you will get your shear force as P by 2 for this small section, very very small. So just at the starting point A, you will have your shear force equal to how much? Suppose P by 2. And what is the sign? It is positive, okay, because it is in the downward direction, so you have to take plus P by 2. Okay, are you able to understand this? Okay, if you are not, let me show you how it is happening. Okay, you are having your beam like this. Okay, your beam is like this. Here you are having P by 2. Suppose you go very very small distance delta x. Okay, and now at this section I want to know what is the shear force. Okay, so draw the free body diagram. This is P by 2. Here you will get a shear force equal to P by 2, and this is your positive direction, mind you. Okay, downward direction is positive, so it will be plus P by 2. Is it okay? So you are having your plus P by 2 here. Now suppose at some general distance x I want. Okay, in this range I want to know what is my shear force. So I'm talking about, okay, I'm rubbing this. Okay, I'm talking about general distance x. Okay, so my first case is x is less than L by 2. This is your L by 2 where your load is acting. So for x less than L by 2, what is the shear force that you will be having? Okay, draw the free body diagram. This will be P by 2. Okay, this is your distance x, and here you will have P by 2. So for x less than P by 2, your shear force will be equal to P by 2. Okay, B part is, suppose your x is greater than L by 2. Okay, then you draw the free body diagram. You will have P by 2 here, P here, this is your L by 2 distance. Okay, and this total distance is x. What is the force that will come here? Think about it. What is the net force that will come at this section? Okay, it is P downward and P by 2 upward. Okay, so this is the resultant will be net P downwards. So to counter that, you will have P by 2 in the upward direction. Look at it carefully. Is it in equilibrium? P by 2 plus P by 2 equal to P. Okay, it is in equilibrium. So you will have a P by 2 force in the upward direction. Since it is upward direction, you will have to take it as minus P by 2. With sign, it will be minus P by 2. So what I am saying here is up to L by 2 distance. Okay, this is your 0, this is L by 2, and this is L. Up to L by 2, you will have constant value of P by 2. Is it okay? Constant value of P by 2. Greater than L by 2, you will have negative value of P by 2. Is it okay? Negative value of P by 2, and then you can just join like this. This is your plus P by 2, and this is your minus P by 2, this is your minus P by 2. Okay, this you can name positive and this you can name negative, and this is your shear force diagram. I hope you are able to understand. This is your classical approach. Okay, now let's talk about bending moment diagram. Okay, let me just shift it downwards. Let's talk about your bending moment diagram, classical approach. Suppose, okay, this is your somewhere 0, this is your center L by 2, and this is L. Okay, bending moment diagram. I am rubbing all this, not required. Okay, suppose this is your beam, this is P. Okay, you know the reactions are P by 2 and P by 2. Okay, let's talk about some distance x from here. Okay, what is the bending moment at this section, red section that I've shown? Okay, draw the free body diagram. This is P by 2. Okay, this is your x. What is the bending moment that will come here? Of course you will have a shear force P by 2, but what is the bending moment? You look here, very simply you look here. This P by 2 force will create a moment like this, P by 2 into x. So to counter this moment, you will have a bending moment in the opposite direction equal to P by 2 into x. Is it okay? P by 2 into x, and mind you, this is your positive direction, so you will have something like this, isn't it? P by 2 into x, it is linear function of x, so you will have something like this. This is for x less than L by 2. Suppose you have x greater than L by 2. Okay, if you have x greater than L by 2, what will be your free body weight diagram will look like? It is P here, your P by 2 here, this is your x. Now can you give me the moment at this section? Moment that is acting at this section. We have already seen you have a shear force. What is the moment for this section? See here, this P by 2 is creating a moment, P by 2 into x. Is it okay? P by 2 into x, okay? And this P is creating a moment, okay? How much is the value? This is L by 2 minus x, okay? Because this is L by 2. Is it okay? So it is in anti-clockwise direction and this is clockwise direction, okay? So minus, okay, rather I am writing clockwise, this is clockwise, so minus plus P L by 2 minus x. Is it okay? So what will you get? Okay. Or rather it is x minus L by 2, right? I have made a mistake here. Okay. This is not L by 2 minus x, this is x. X is total length minus L by 2. Okay. So this mistake I have made, correct it. This is your x minus L by 2. Now you sum it up, you will get it as, this will be Px by 2 minus Pl by 2. Okay. This is the resultant moment, but whatever moment is produced here, it will be resisting this moment, so it will be opposite in direction. Okay. So you reverse the sign, you will get Pl by 2 minus Px by 2. This is your resisting moment. Okay. And its direction will be something like this. Is it okay? So if you see the variation, it is declining with x, so it will look something like this. Is it okay? Just the line of equation you have to apply. Okay. What is this value here? Center value. Okay. Here you are having Px by 2 moment, right? Px by 2 moment you are having. Put x equal to L by 2. How much you will get? Pl by 4. So this maximum value here is Pl by 4. Is it okay? This is the simplest possible question in shear force diagram and bending moment diagram. Okay. So I hope you understood. And this is your classical approach. Okay. This is not a shortcut approach. This is your classical approach. We will never follow classical approach unless we are stuck in some question. We will never follow classical approach. We will always follow the shortcut approach. Okay. What is the shortcut approach? For shortcut approach, you have to consider a couple of cases. Okay. If you can remember those cases, you will be able to draw shear force and bending moment diagram very quickly. Okay. Suppose you have some loading here P and you have some V1 load here and some V2 loading here. Is it okay? I want you to draw the shear force and bending moment diagram. Okay. Here you will draw shear force and here you will draw bending moment diagram. These are some basic cases. You have to remember these cases, how I am drawing this. Okay. So how I am drawing this? Suppose you have V1 here. Is it okay? V1 here. So V1 is in upward direction. Okay. So when you are drawing shear force diagram, you just draw here V1 in upward direction, positive. Is it okay? In this span, okay, in this blue span, there is no loading, isn't it? Earlier we have derived one relation. W is equal to dV by dx. Is it okay? W was your loading. I am saying that in this region there is no loading. Since there is no loading, your W is equal to how much? 0. That is equal to dV by dx. Okay, if you integrate, what will you get? dV is equal to 0 dx. If you integrate, you will get shear force is constant. Is it okay? Your shear force is constant in this region. Okay, from here to here, your shear force is constant and it is equal to V1. Okay, so draw in that region. Okay, is it okay? Okay. Now rather than moving from the left side, you move from the right side. Okay, you move from the right side. What you do, this is your V2, is it? This is your V2 and V2 is also in upward direction. So what you can do here is you can produce V2 in the upward direction. Okay, here also there is no loading. So no loading will mean that your shear force is constant. Okay, so you draw your shear force like this. Is it okay? you draw your shear force like this. Is it okay? Is it okay? I hope it is okay. Now there is another way to draw this. Okay, another way to draw this. In this you may get stuck sometimes, so there is another way. When you came here, okay, up to here it was constant, then you encountered this loading P in the downward direction. So what you do, you shift it downward by a value P, and then it is constant, so this will automatically be V2. Okay, so this is how you remember it. Okay, whenever you encounter a downward constant force, you reduce your shear force diagram by that value. Is it okay? Come to bending moment diagram. Okay, bending moment diagram. We have seen a relationship between bending moment diagram and shear force diagram, or rather we have seen a relation between shear force and bending moment. Okay, what is that relationship? V is equal to dm by dx. Okay, what is this dm by dx? Is it the slope of bending moment diagram? Dm by dx is nothing but the slope of the diagram we want to draw. Okay, so your slope diagram that we have already drawn, okay, in this region your slope is constant, is equal to V1. In this region your slope is constant and is equal to V2 for bending moment diagram. Is it okay? Now I don't know the value here. Okay, here I don't know the value, ends, it may be anything. Okay, but I know this thing that in this region I have a positive slope. Okay, positive slope. Okay, V1 is constant and positive. Okay, suppose I am writing V equal to C, some constant. So what will your moment will be? C into x plus C2. Okay, is it a linear equation? Okay, so you can say that it is a linear equation and it has positive slope, so it will be something like this. Is this okay? Again you have V2 here. V2 is also positive, but it has having some less slope, so I think it will be something like this. Is it okay? So this is what your bending moment diagram will look like, and this is how you are going to draw this. Okay, so the shortcut that we follow is basically we use these relationships, W is equal to dV by dx and V equal to dm by dx, to draw our bending moment and shear force diagrams. I hope it is clear. Let's see a couple more cases. Let's see a case of concentrated moment. Okay, suppose you are drawing a case of concentrated moment. You have m1 here, some moment m prime here, and some moment m2 here. Is it okay? Now I want you to draw bending moment diagram and shear force diagram. Okay, don't worry if you are not able to understand. We will do many questions, so you will get very fluent in bending moment and shear force diagrams. Okay, what is W? Is it dV by dx? Okay, do you see any loading in your span anywhere? There is no loading in your span anywhere. W is 0 throughout, and your shear force is equal to W is 0, so your dV by dx is 0, so your V is constant throughout. Your shear force is constant throughout. What is that constant value? Look at this end. At this end your shear force is 0, so your shear force will actually remain 0 throughout. Okay, shear force is 0 throughout. Okay, is it clear? From this equation you can see W is equal to dV by dx. There is no loading on this span, so W is equal to 0, so your shear force is constant throughout your span. What is that constant value? That constant value is whatever you are having here at this node. Okay, at this node you are not having any reaction, so you have 0 value, so throughout it will remain 0. Okay, I think it is simple, you will be able to understand. Let's talk about shear force diagram. I have already told you V is equal to dm by dx. Okay, V is equal to 0, so dm by dx is 0, so moment is equal to how much? It is constant. It is constant. Now you see this somewhere here. If I want to see, suppose AA section, you are having m1 here, so resisting moment you will get m1, isn't it? Resisting moment you will get m1, and mind you it is positive, so you will have constant moment m1 here up to this point. Is it okay? Suddenly you have encountered an anti-clockwise moment here, m prime. Okay, so that will reduce this value by m prime. Is it okay? And then you will continue with your mt. Okay? These are constants. Okay, these are not slant, these are constant. Okay? This is also constant and this is also constant. So this is what your bending moment diagram will look like. I hope you are able to understand. Moving on to the third type. Suppose you are having a UDL. Suppose you are having a UDL like this. Okay, this is pin joint, or rather using a pin joint. Okay, you are having some shear force V1 here, some shear force V2 here, some moment M1 here, and some moment M2 here. Is it okay? Now you have to draw the shear force and bending moment diagram. Shear force diagram here and your bending moment diagram here. Let's start with the shear force diagram, whatever we have learned till now. Okay, I have told you at the end or at the support you are having V1 value in upward direction, so just increase, okay, your shear force diagram by V1. Is this clear? This much you can do. Now use the equation. W is equal to how much? dV by dx. What is the value of W? It is some constant value, okay, constant value throughout your span. It is in the downward direction, so I have to use minus W. Is it okay? Downward is negative, so minus W is equal to dV by dx. So your V will be something minus Wx plus constant, isn't it? Minus Wx plus constant. So you can say it will be a linear value coming down like this. Okay, isn't it? Coming well down like this, and it will end up to V2. Okay, this is your shear force diagram. Is it okay? This is your shear force diagram. Next, let's draw our bending moment diagram. For bending moment diagram, you know at the end you are having moment M1, so just increase this by M1. Okay, and here you are having your M2. In the middle, what is happening? Shear force is equal to dm by dx. Now your shear force is following linear relation. Okay, linear relation. So obviously your moment will follow x square type relation, isn't it? If you put it here and you integrate, what will you get? Obviously you integrate x, so you will get x square, isn't it? So it is following some x square type of relation, so your curve will be parabolic. In this half your slope is positive, in this half your slope is negative. Okay, slope is positive and it is decreasing, isn't it? So you will have something like this, or rather I have to create some space here. Okay, this is your length. Here you are having some m1 value. Okay, and now I am saying it is parabolic with positive slope. Okay, the slope will become 0 at this point, so it is having positive decreasing slope, and it will be something like this. Here you have negative, okay, negative increasing slope, so it will be something like this, and here the value will be m2, whatever you are having here. Is it okay? This is what your bending moment diagram will look like. I hope you are able to understand. Very, very simple. Is it okay? Let's see one more case. Fourth, you are having something like this. Suppose you are having a trapezium type of loading, something like this. Okay, you are having some shear force V1 here and some shear force V2 here. Okay, and some moment, suppose M1 here and some moment M2 here. Is it okay? I want you to draw the shear force and bending moment diagram. Shear force diagram is here and bending moment diagram is here. So again follow the same procedure. You have positive V1 here, so increase your value by V1. Okay, and then you have some loading. Use the equation W is equal to dV by dx. Now your W is not constant. It is in the downward direction, but it is not constant. It is following a linear relationship. It is equal to minus W, something a function of x plus c, something like this. this is the value of your w, is equal to dv by dx. If you integrate v, you will get some c1x square plus c2 type of situation. So your shear force is a parabolic curve. Shear force is a parabolic curve. Now see here, just you have to see this equation and you will be able to draw. Okay, dv by dx is what? dv by dx is nothing, it is the slope of shear force diagram, which is equal to your w, and your w is increasing with distance, so your slope is also increasing with distance. Is it okay? Your slope is also increasing with distance, so I am drawing it something like this. It is parabolic and slope is increasing with distance, so it is something like this. Okay, it is literally more curvy, slope will continuously increase. Here you will have your value v2. Is this okay? This is your shear force diagram. Now to draw the bending moment diagram, obviously I know one thing. Okay, at the corners here you are having value m1, okay, and here you are having some value m2. You can obviously say that v is equal to dm by dx. Okay, v is following parabolic curve or square curve, so your m will be cubic, isn't it? If you integrate this value x square, you will get x cube, so your m is cubic. Okay, and your slope is constantly, it is positive but it is reducing, isn't it? It is positive but it is reducing, so I think it is something like this. It is something like this. Slope is positive but it is reducing with your distance, isn't it? So this will be your bending moment diagram. So I think these 4 cases are the basic cases that you should know. Now you can draw any bending moment diagram. I have told you the key thing is these equations, v is equal to dm by dx and w is equal to dv by dx. Just you have to look at these equations and you will be able to draw the bending moment and shear force diagram. Is it okay? Is it okay? I want to tell you one more thing about calculation of moment. Okay, calculation of moment. Calculation of moment. Calculation of moment means, suppose you are having some pin joint here, roller here, and you are having some P here. Is it okay? Suppose I have drawn the shear force diagram. Okay, I have drawn the shear force diagram. I already know that shear force diagram will look something like this. Okay, just now we have drawn it, P by 2, and this is your minus P by 2. Okay, can you tell me the moment at the point A, center, okay, without drawing any bending moment diagram? Can you tell me the moment at A without drawing the bending moment diagram? Can you tell me? Think about it. You have this relation, v is equal to dm by dx. This relationship is very powerful. You see, dm is equal to how much? V dx. Okay, I am integrating between 2 points from A to B. A to B. Okay, so it will be mb minus ma is equal to integral A to B v dx. This is a very powerful relation. Okay, this is a very powerful relation. If you look closely, okay, what is this value? This is the area under shear force diagram between A and B, isn't it? mb minus ma is the moment at B minus moment at A. Suppose my A point is here. This is my A, and this is my, rather than naming this A, I am naming it B. Okay, this is my B. This is my A, this is my B. Now, I know one thing for sure. My moment at A is 0. It is pin joint. Okay, pin joint. So pin joint does not have any moment. So I know for sure that my moment as A is 0. Okay, I am using this relationship. Now I can say moment at B minus moment at A is equal to area under the curve. Rather than writing integral, I am just writing, okay, area under SFD, okay, between A and B. That means this area between A and B. Okay, so what is this area? Is it P by 2 into L by 2? Okay, this is your L by 2 and this is your P by 2. This is a rectangle, so you can say the area is P by 2 into L by 2. MB you want to find out, MA is equal to 0, so you can say that MB is equal to PL by 4. Is it okay? PL by 4. This approach may look a little stupid for this question because you already know the answer, okay, but imagine this approach is very powerful, okay. In big questions you will have an edge over other people, you can solve it very quickly. Suppose a shear force diagram is very complex, something like this, okay, shear force diagram, this is your shear force diagram, okay. Now this is your point A, this is your point B, okay. Suppose you know the moment at A, you want to find out the moment at B, okay. To save some time, you can directly write MB minus MA is equal to this area, shaded area. From this, very quickly you can calculate your MB. Okay. Depending on how quickly you can calculate the area, some of the areas you can directly remember, okay. Suppose you have this type of parabolic curve, okay. This is your A. Okay, this is your B, so I think this is 2/3 of AB, isn't it? 2/3 of AB it is. Okay, triangle area you know already, half into base into height. Okay, this is your height, this is your base, so it is half into BH. Okay, simple areas you can remember. Your rectangle area you know B into H. Okay, so if you remember these areas, it is very simple that you can calculate your MB minus MA. I think this is all you need to know to draw shear force and bending moment diagram.